Good afternoon and welcome to another seminar for structural engineers. This is aimed at graduates, but anyone wanting to know a little bit more about structural engineering. It's always useful. And this is taken from the New Zealand Building Code B1 VM2. And for the sharp-eyed, you'll notice it used to be VM4. They've taken out VM2 and VM3 and renumbered them. So we're going to be looking at the geotechnical design of pad foundations in accordance with the New Zealand Building Code, in particular concrete pad foundations. And we're going to be looking how the stress is distributed underneath a concrete pad foundation and how we work out effective breadths and effective widths and so on, and determine what the allowable or design bearing capacity of the ground is underneath your pad foundation. And yes, it's another seminar asking what the hell does this spreadsheet do? So yes, Redco have a whole load of spreadsheets and one of them covers the design of pad foundations. And we're going to explain them not in the spreadsheet, but using Mathcad instead, because they're nice big numbers and a long form explanation, like you would do a hand calculation. So here it is, as simple as it gets, and this is a typical concrete pad foundation. These are, in this case, they're isolated pad foundations with a concrete column smack in the middle of it. Doesn't get much simpler than that. And the reinforcement is relatively straightforward. You've got some tension bars in the bottom in both directions. In this case, we've got starter bars out for the column. Now, the stress underneath the pad foundation can be quite complicated, and you'll end up with diagrams looking like this. Today, we're not going to be looking at this. We're just concentrating on the stress directly beneath the underneath surface of the pad foundation. So yes, the stress in the ground is complicated, but we don't really need to pay much attention to that today for the purposes of designing a concrete pad foundation. In a simple case, you've got your load coming down onto your pad foundation. It's distributed as if it's a strut and tie model. And we can sometimes assume that your stress underneath the concrete pad foundation is uniform. If your load is eccentric or you have a bending moment applied to the pad foundation, then you won't have a uniform stress distribution, but we simplify it to say we have a linear stress distribution. So moving from left to right, we've got a simple concentric load giving you a uniform load underneath, and so the stress underneath is just the load divided by the area of the pad, and our eccentricity is 0. Now, if we start applying moments or apply the load eccentrically, then we have a linear, or we assume there's a linear stress distribution going from a maximum to a minimum. And we can work out, well, we've got our applied axial load divided by the area, but we've got this extra feature here, and that's basically distributing the bending moment. So it's the moment divided by Z in a word. If you look at that, that's the section modulus of the base, so BD squared over 6. Now there's this magic number here, D over 6. So if our eccentricity is less than or equal to D over 6, then we have no uplift in our base and our base is fully effective. This is the magic middle third rule. Now, if we go beyond that, then we start getting uplift. And the way we get around that is we ignore the areas which are subject to uplift, and then we work out an effective area of our concrete pad foundation. So a reminder of the types of soil, we've seen this before in previous examples. We can split them into cohesionless and cohesive soils. So for cohesionless soils, we just look at long-term analysis and these effective stresses and strength parameters. For cohesive soils, we've got to do the design twice. We've got a short-term analysis using undrained shear strength of the clay subjected to total stresses. In the long term, we assume it's drained, and therefore we look at effective stresses and use the strength parameters of effective cohesion and effective angle of shearing resistance. And so our diagrams look a little bit like this for undrained conditions, and like that for drained conditions. So in undrained conditions, your SU, as we call it, is greater than 0. In drain conditions, we can see that our cohesion goes down to 0, but we have an effective angle of shearing resistance greater than 0. And these are the two important parameters which drive the design of your base, and it determines the ultimate bearing capacity of your ground. For reference, this is the new version. This is B1 VM2, formerly VM4. What's the difference between this and the old one? Well, it's been renamed. It's now the Geotechnical Design of Foundations, and it's been renumbered to VM2. It's been restructured and renumbered, but the content is mostly the same. Now, I say mostly because they've missed a bit out at the end. They haven't provided the examples that the previous edition did. And also to hand, you should have the loading code. So it's NZS 1170 and the various parts of that. So this code, VM2, is deliberately designed to be used with NZS 1170. A reminder of our building code regulatory system and how it all stacks together. Right at the top, we've got the Building Act, and underneath that, you've got the Building Code. And the Building Code is taking precedence over pretty much everything else underneath, including the alternative solution, the acceptable solutions, and in our case, the verification methods, VM, and we are VM2. The building code covers everything from structure to energy to drainage to so on, and it moves from part A through to part H. The one we're interested in is the part B. Now, what you need to know is what's not included in VM2, and all of these activities, so site investigation, serviceability, slope stability, liquefaction and vibration, are not included in VM2. We are just looking at the simple design of, in this case, pad foundations, but it also covers retaining walls and piles. And what you need to do is talk to your local friendly geotechnical engineer to have insight onto all of these items. So how do we use VM2? Well, obviously you need to use it in combination with the other parts of the building code, in particular B1 VM1, that's for the superstructure. And you take your strength reduction factors and you use them with the design factors given in the various loading codes. And should go without saying, but it helps if you know what you're doing. So this document needs to be used by someone who has experience and qualifications in the area of design of foundations. And it's linked with the design of the superstructure, which is in VM1. You can be shallow or deep in your foundations. And in this case, they define a shallow foundation in one which the depth from the ground surface to the underside of the foundation is less than 5 times the width of the foundations. Now, other countries have different definitions of that, but a similar principle. Anything bigger than that, then you're looking at a deep foundation. You have to consider the worst groundwater when you're doing a design, and the groundwater has quite a big impact on the design of your footing. So, as we've said before, the foundation strength for cohesive soil depends on the loading duration, whether consolidation can occur or not. That's why we make a distinction between short-term and long-term loading. And so a reminder, short-term loading is that stuff which is earthquakes, winds, and so on. And long-term is looking at permanent loads, including the dead loads. So for short-term loading, no consolidation occurs, and the calculation is in terms of undrained shear strength and total stress. For long-term, we assume it's drained, and then we look in terms of effective stress and the effective angle of shearing resistance. For cohesionless soils, that's like our sands and gravels, then consolidation occurs very quickly, so we just look at the drain strength in all cases. And again, we're assuming that the construction is going to be done under supervision and that we can verify these soil parameters during the construction period. This is a table taken from VM2, and this gives you your bearing strength factors for shallow foundations. Note there is a different diagram for your deep foundations. You should also note that this is a log scale on the left-hand side, and it also on the left-hand side doesn't go down to 0. So at the bottom of your diagram, you'll see some notes that if the angle of shearing resistance is 0, then your NC is 5.14. Well, you could just about see that. And then your NQ is 1. You can just about see that too. But your N gamma is off the scale. And so they just shove it in as 0. Now you can take it off the diagram or you can work it out. So they give you the equations to work it out. But there are a whole load of fiddle factors, as I like to call them. They're lambda factors, beginning with the shape factors. So you've got lambda CS, lambda QS, and lambda gamma S. And these are dependent upon the shape of the foundation, so your effective length, effective width, and the angle of shearing resistance. You've got depth factors, so naturally it depends on how deep your foundation is relative to the width of the foundation as well. The load inclination factors, so even if you think you're applying vertical and horizontal loads, the resultant force is going to be on the incline. So therefore you need to calculate these load inclination factors, lambda CI, lambda QI, and lambda gamma I. And it varies depending on which direction your loading is. So loading parallel to the effective length is in one equation, and loading parallel to B is determined by another equation. You've got ground inclination factors. So if you're not on level ground, you need to calculate by these equations the lambda CG, lambda QD, and lambda gamma G. So for horizontal ground, all these ground inclination factors are 1. So here is our spreadsheet, and it comes under the templates. So basically, the most engineers will look at the first page or the first 2 pages. So we put in our parameters in there, and hey presto, we've suddenly got our stress underneath. And so the capacity of the section is given here. There's probably another page that most engineers probably don't look at, and that is this one, to determine the actual geotechnical parameters that you're using to determine the bearing capacity. Another useful feature of this is it determines the strength of the pad as if it were a concrete slab. So it determines what the rebar is. Now, we won't be doing that for today. We'll be looking at primarily the geotechnical design. The concrete section design is referred to another part of the code, and that's simply follow the concrete code and you'll get the design just as it is in a slab to define your tension reinforcement and your shear reinforcement if required. So let's go to the Mathcad and explain that all in long form. So here is the Mathcad for a concentric pad footing in cohesionless soils. So some of the assumptions I've stated before in the body of the seminar. So what we're going to be considering here is just 2 ultimate limit states. That's the long-term bearing capacity failure of the foundation and the long-term sliding at the foundation level. We're not considering earthquake loading. You could do, but that's another exercise. So you need to modify what the loading is and the geotechnical parameters suitable for earthquake loading. So a reminder, long-term analysis is done using effective stress and uses strength parameters, the effective cohesion and the effective angle of shearing resistance. So we begin by putting in our parameters for the footing. So its breadth, its thickness, its length, and the depth to the underside, and the unit weight of the concrete. Then we're putting our loading. So we've got vertical loading and we've got horizontal loading about each direction. And then we put in our soil parameters. So we're saying we're on sandy gravel. So we've got our effective stress cohesion as 0 and our effective angle of shearing resistance as 30. We've got our unit weight of soil and gamma S as 18, but we have an effective weight of soil potentially as 8.1, depending on where your water table is. We can calculate our passive earth pressure, Kp as 3, and that's given in B1 VM2. We can pull out the strength reduction factors for static bearing, passive earth pressure, and static sliding pressure, sliding failure from the code. So we start with the total stress and then get the vertical stress in the ground. And because we've got poor water pressure in there, the effective vertical stress is slightly lower than the total stress. We derive our design loadings. Well, first of all, let's work out what the weight of the concrete foundation is, the weight of the backfill above the foundation, and then the resultant, we've got a resultant horizontal load as required. But our resultant reaction, our vertical reaction R, is just simply the sum of the applied load with the weights of the foundation backfill on top. And that's worked out as 48 kilonewtons. So I've recycled the old diagram from the VM4. It's pretty much the same in VM2. And this shows you your plan of your rectangular pad foundation with an eccentric load. And it tells you that part of your pad foundation is effective and another part is not effective. And that's why we have an effective length, L dash, and effective width of B dash. But to calculate those, we need to work out what the eccentricity is. So we've said that the water pressure acting on the underside of the foundation is 4 kPa, so our effective vertical force is reduced because of that poor water pressure. Taking moments about the point load, the eccentricity about the breadth is 79 millimeters, and about the length is about 10 millimeters. So your effective length of the foundation is 880 millimeters. And the effective width is 742 millimeters. You can do a quick check as to whether those dimensions are within the middle third. So compare the L-/2 with the actual dimension over 6, and then we go OK. If we're not, we need to go back and do some adjustment to the size of our pad foundation. So now we look at the effective area of the foundation, A dash, based on the effective width multiplied by the effective length, which gives us a design bearing pressure, i.e. the applied bearing pressure of 68.5 kilopascals. Now this is where we get into complicated calculations, but these calculations are taken from the code VM2. This one is a bit obscure because you're raising the natural logarithm by pi times tan phi and then multiplying it again. So you've got to be careful how you write that to get the correct answer. And if you want, check it against the diagram in the code. So we have NQ, which is worked out as 18.4, NC is 30.1, and N gamma is 20.1. So here are the calculations for the shape factors. Lambda CS is 1.5, lambda QS is 1.48, and lambda gamma S is 0.663. Our ground is level, so therefore all the ground inclination factors are 1. We have our depth factors. Now we have a choice on our depth factors depending on the depth to width ratio. And because our depth to width ratio is less than 1, we take the first value, which gives a gamma QD of 1.23. And lambda CD is worked out based on the lambda QD as 1.25. And lambda gamma D is 1. So our load inclination factors, again, vary depending on which direction you're loading. The horizontal load in one direction, the length, works out as 0.978, and in the width, it works out as 0.675. For convenience, I just take the smallest of those because these numbers are going to be used to multiply your factors together to reduce your potential ground bearing capacity. So then we get to this very long equation, which is given in the code, and you add up all of those numbers and multiply all those factors together, and you get an ultimate bearing strength as 168.1 kPa, which gives you a design bearing strength of 75. Note this is significantly lower than a good ground value. Our capacity divided by our applied load is greater than 1, so we're okay. The next ultimate limit state we need to consider is the long-term foundation sliding failure. So we've worked out that our coefficient of passive earth pressure is 3, and that is going to be used down in our passive resistance. But our sliding resistance is based upon the cohesion under the base, plus the effectively friction underneath the base. So our sliding resistance because of the base is a mere 25.8 kilonewtons. Now, passive resistance, you'll notice the first part of that equation is a simple passive resistance against the face of the foundation. There's this extra factor which is taken from the old version, VM4, and it's given in the example. Now, this doesn't appear in VM2, so if you want to be conservative, take it out, and it'll rework it out as to a reduced capacity. And our C#, as it were, our effective cohesion is 0, and therefore our passive resistance works out as 4 kilonewtons. So we've got a design sliding resistance when we put in our strength reduction factors of 22 kilonewtons in length and 22.4 in the width. So in both cases, they're okay. So that's the pad foundation for concentric loading in cohesionless soils. I'll move on to the pad foundation for eccentric loading in cohesive soils. So we've got a bit more complicated, and we've got more work to do. So we're looking at 4 ultimate limit states considered. First of all, we've got a short-term bearing capacity failure of the foundation, the short-term sliding of the foundation, then the long-term bearing capacity and the long-term sliding capacity. Again, we're not considering earthquakes here, but you could do if you add the loading and modify the geotechnical parameters and the strength reduction factors to take into account earthquake loading. So once again, we put in our input data, the breadth, width, length, thickness of the foundations. In this case, it's 2 meters wide and 3 meters long. The difference here is we're applying our load eccentrically, so it's not in the middle of the foundation. And we've got design vertical loads and horizontal loads, significant loads in both directions. And we're also applying moments. Now our soil parameters, we've got 2 lots of soil parameters. We've got our short-term values. So we've taken SU, which you should get from your geotechnical engineer. SU is 75, and the unit weight of the clay is 18. And then in the long term, we're looking at the effective stress cohesion as 12.5, and the effective angle of shearing resistance as 25. Again, we work out our coefficient of passive earth pressure. In this case, it's 2.4. We've also got sand, so we've got backfill over our pad foundation, and we can add the parameters for that. What we're really looking for is the unit weight, because we're just concerned about the dead load applied. Here is our effective area diagram again and how we work it out. So on the left, we have the plan showing the effective area, and on the right, we have a calculation for the eccentricity. So in this case, you're looking at a cross section through the foundation. Here is our resultant upward force. Here is the applied moment, and here is the eccentricity from the position of the applied load. We take our strength reduction factors as before from the code, and we work out the total stress in the ground at the underside of the foundation. We derive our design loadings. So we've got our weight of the foundation, the weight of the backfill. With that, you can add that to the applied vertical load to get a total vertical reaction of 374 kilonewtons. Taking moments about the point of loading, you then work out what the eccentricity is about breadth as 125 millimeters and about the length as 139 millimeters using these equations. And these are given in the code, which then gives you your effective length of the foundation as 2.27 meters. It also gives you the effective width of the foundation as 1.749 meters. And in both cases, we can check whether the eccentricity has meant that the resultant load is still within the middle third. So we've got a relatively balanced foundation. And if it isn't, you need to redesign your foundation dimensions to suit. Our first ultimate limit state check is on the short-term static foundation bearing failure. So we've got a design bearing pressure of 94 kPa. Now the code gives us a bearing strength factor NC of 5.14 because our effective angle of shear resistance is 0. We can work out the rest given that as NQ and N gamma as 1 and 0. We've got our shape factors and we've got our ground inclination factors. We've got horizontal ground, therefore they're all 1. We've got our depth factors, and again we check, depending on the ratio of the depth to width, which factor to take. And then we've got our ultimate bearing strength as QU as 504 kPa. So our design bearing strength is 227. It's bigger than the applied, so we've got a utilization ratio that's fine. Going on to our second check, which is our short-term static foundation sliding failure. So this is a similar approach to before. We're just looking at the adhesion effectively underneath the pad foundation and multiplying it by the area. We also add the passive resistance in both directions. And again, this is the cohesion multiplied by the thickness divided by the length. And then you've got your resistance given by B1 VM4. Again, if you want to be conservative, take that out in both cases and see if you're still okay. And so our design sliding strength is 300 in the width and 286 in the length. So our capacity divided by our load is well over 3, so we're good to go. Our third check is on the long-term static foundation bearing failure. Again, we work out what effective vertical force is. And this time we take into account the pore water pressure underneath. And we work out what our eccentricities are again, because our effective vertical force is different, which gives us an effective length of 2.29 and effective width of 1.73. So these are slightly different from the short-term values because we're now taking into account pore water pressure. Now, because the depth of the groundwater isn't particularly deep, the figures are not hugely different. However, if you are a much deeper foundation with a much greater height of groundwater, then there can be a big difference. And if it's deep enough, you might even get uplift from buoyancy. So we check whether our effective width and our effective lengths are within the middle third. We found that they're good, and derive our effective foundation area and our design bearing pressure based upon the resultant force divided by the effective area. Here are our recalculated bearing capacity factors. Now that we're looking at an angle of shearing resistance, and we work out the shape factors again, work out the ground inclination factors are still 1, and our depth factors are worked out using those values. Again, rework out what the load inclination factors are, because we've got different values for our reaction and different values for our effective areas. And we put it into the very long equation again and work out that our ultimate bearing strength is 382, so our design bearing strength is 171.9, so it's significantly higher than the applied bearing strength, so we're okay. And the fourth and final check we do for today is the long-term foundation sliding resistance. And so our sliding resistance at the base is again the cohesion underneath plus the friction generated from the vertical reaction. We look at the passive resistance on the footing face and calculate it as normal. And if you want to be conservative, take that value out there, which has been borrowed from B1 VM4, the previous edition. It makes a little bit of difference, but usually not enough to put you over the edge. So it reduces our factors of safety in this case. So our total design sliding strength is 172, and our sliding strength in the long direction is 172 as well. So our factors there are going to be 2.2 and in both cases. So that was the Mathcad. Seen that, we've seen that. Now, what about uplift? In some cases, particularly if you're dealing with portal frames, you might have uplift on your column bases and you need to resist it. If you don't resist it, then your structure is not in equilibrium and you've got a moving mobile structure. So hopefully your self-weight of the footing should exceed the uplift forces. If it doesn't, you can take into account the weight of the ground beam that's usually attached to your foundation or footing. And if that's still not enough, you can add in the weight of the slab, but be careful when you're doing that, because you can only add in the weight of the slab if that slab is able to take the additional moments which you get from the uplift. So you can imagine this, if you've got a thin slab with an uplift forced on it, you're going to induce moments in there. And if you've got very light reinforcement, it may not be able to take it. So just watch out for that. Site investigation and the bits that's missing from the code. So VM2 doesn't give any information about site investigation, but it's telling you that you do need to investigate your site by a person of suitable expertise and experience, i.e. usually a geotechnical engineer. And your friendly geotechnical engineer should produce a friendly geotechnical report which contains all those soil parameters that you need to design your foundations. It needs to tell you what your effective angle of shearing resistance is, or your cohesion and so on, as well as your unit weights in your soil, the type of soil you're dealing with, and any presence of groundwater. Settlement. Now, VM2 says it doesn't deal with settlement, but that's not entirely true, because your bearing capacities are really geared towards settlement rather than actually strength. And what you're trying to do is limit the differential settlement. And so if you've got a number of pad foundations, you want to limit the settlement between them to no more than 25 millimeters over a horizontal distance of 6 meters. Or you need to design your structure that it doesn't get damaged when your excess deformation exceeds 25 millimeters on that 6 meters. So finally, the references, and we'll pause for questions.